Yes. No? Well, I think that we can then start with this afternoon session. And the next talk is by Dr. Haoyu from University of Texas, Austin, USA. And the title of the talk is Probing p-Adic conformal field theory using p-Adic, but I cannot see it, and projective GL2.
Okay,
you can start.
Okay, thank you, Branko, for the introduction, and thank you, Wilson, for organizing this conference. And it is a great opportunity to speak here. So today I'll talk something about probing p-Adic CFT in the context of p-Adic holography. So this is based on the work appeared about 1.5 years ago. It is done with Stephen Abbott, a grad student at UCLA, and Mongyang Zhang, an undergrad at Berkeley back then, and now a grad student at Princeton. So here is the archive number. So first, let me talk about the motivation of studying the p-Adic holography and in physics. So I guess.
Sorry for interrupting. I am seeing a message downloading p-Adic Mexico. It's a small window, and this window is appearing in the recording.
Oh.
Yeah, yes, I also see. Okay, it's now better. Now it's better. Okay.
Now it's better. So okay.
Yeah, you can continue.
Okay, sorry, that probably it's an earlier version of the slide showing up. So first, let me talk about the motivation. So the p-Adic holography is a nice way to get a discretized space-time model, which is as similar to ordinary ADS space-time as possible. It's unlike other toy model like tensor networks. And the advantage of doing p-Adic holography is that many techniques in the usual holography carry over, such as propagators, Witten diagrams, and the GKPW dictionaries, etc. So it is partially inspired by the success of p-Adic string back in the 80s. And I believe the conference has been devoted to some aspects of p-Adic strings. So the main contributors are as follows, and Branko is here. And,
yes.
Among many others. Sorry if I haven't cited every contributors. So the nice key result of the p-Adic string program is that we can express the Veneziano and the Shapiro-Versor amplitudes in the p-Adic settings, and they enjoy a nice idyllic product. And I believe Bogdan's talk has alluded to it. And the p-Adic field theory enjoy connections with strongly correlated condensed matter system. So for example, the ultra cold atoms. So it is a collaboration between Gabsa and the experimentalists. So they propose some experimental proposal to detect this non-Kimenian geometry underlying the ultra cold atoms. And I would like to also mention that there's an earlier work on connection between the zeta CFT and BD3. So it is making analogy between the BD3 and eternal inflation. It is the work done by the Stanford group back in 2012, but this will not be our focus today. And basically the pioneering paper for the modern p-Adic holography are these two papers. The first one by the Princeton group, and the second one by the Caltech group. And I think Sasak is here, and Bogdan is our previous speaker. So since this is a p-Adic conference, I guess I don't need to make too much introduction to p-Adic, but I would like to do so just for the sake of self-consistency. So at first glance, it is a somewhat weird number system to physicists. So there are two key properties enjoyed by the p-Adic number system. So first is a non-Archimedean property. So pictorially, if you have one larger and one smaller element, and if you accumulate enough number of the smaller element, you will never succeed the larger one. So intuitively, you can think as the tortoise can never take over the hare. And also there's an important property called ultrametricity, namely this inequality. So again, pictorially, if you draw triangles over p-Adic fields, then all of them are tall isosceles, because otherwise the key axiom, the triangle inequality, would be violated. And the basic idea behind the p-Adic system is that we view the prime number p as a small but non-zero number, so that we can do productive expansion somehow. And all integers co-prime to p have the same size. So for prime number p, qp is the completion of rational numbers with respect to the p-Adic norm. And any p-Adic number has a unique expansion as follows. So it is different from the usual digital expansion. We should read the expansion from right to left. And each digit takes value from 0 to p minus 1. And v sub p in the lower bound of the summation is the smallest integer index such that the a sub v sub p is non-zero. And now the p-Adic norm, or more precisely the p-Adic absolute value, is defined as 1 over p to the v sub p. And there's an Ostrovsky theorem saying that the rationals only has two completions. One is the rational number, and the another one is the p-Adic number we're talking about. So the BT tree, I believe the audience has seen it many times in this conference. So it is a great visualization of p-Adic numbers, and the T sub p tree has valence p plus 1. And in the community of statistical mechanics, it is also called the base lattice. And it is also it appears in this famous monograph by Baxter. So it is first introduced into the high-energy community by Zabrodin, which also alluded to by Bogdan. So it's the interior of an open string worksheet. It is a non-compact space, but we can identify the asymptotic boundary as the projective line over Q sub p. And the isometric group is PGL2QP. It will be the key player in the p-Adic holography. And it is straightforward to draw the BT tree for the unramified extension, which is an n-dimensional vector space over Q sub p. And for a parallel introduction to BT tree, I refer you to talk on Tuesday by Ling Yan and a later talk by Malik. So there are several definitions of BT tree. Like the first one is a more formal one. So it is based on this two-dimensional QP lattice. If we consider a general vector in the lattice L, where U and V are independent basis vectors, we say that L and L prime are equivalent if they only differ by a multiplicative constant, which is non-zero. And to construct the BT tree, we assign each equivalence class to a vertex on a tree. And the matrix GL2Q, matrix in GL2QP acts on the lattice as matrix multiplication. And generically, the group takes one equivalence class to another. But we further notice that any subgroup conjugate to PGL2ZP leaves the equivalence class invariant. So the BT tree should really be in a homogeneous space, PGL2QP modded by PGL2ZP. So latter being the maximally compact subgroup. So now we have the vertices of the tree. We need to connect them. And sorry, is there a question? Okay. Okay, I'll move on. So given the vertices, we need to draw edges to connect them. And it is straightforward in this prescription because as long as the lattice L and L prime are incident, namely satisfying this inclusion condition, we draw an edge between them. So this is quite abstract, and we would like to resort to a more intuitive definition. So this graphical definition is, I think it appeared before 2016, but for physicists, it was popularized by this pioneering paper by Gabser and his students. So let's look back at the p-Adic expansion of any p-Adic number. And so in order to move up in the BT tree, we choose a digit in the expansion from right to left, starting from the decimal point. And after leaving this red trunk, each node is a rational approximation of the would-be p-Adic number. So it is easy to see that this tree has valence p+1 because in order to leave the trunk, you should choose the rightmost digit. Namely, you have p-1 choices and plus the forward branch and the backward branch, you have p+1 valence. And for other nodes, you can have p choices because they are to the left of the rightmost digit. And here are just some notations which will be useful in the following discussion. So in summary, so our results in summary are as follows. So first we computed the partition functions of p-Adic quote unquote thermal ADS and BZ black hole. And then we use the p-Adic genus 1-point functions, which is the CFT 1-point function in the semi-classical background of p-Adic BDZ. So there are, which leads to some results we believe to be universal for p-Adic CFT. And finally, which is quite separate from the first two bullet points, we set up certain criteria to pinpoint the group representation of PGL2QP for p-Adic CFTs. So any questions so far? Okay, then I'll talk more about p-Adic holography, the background of p-Adic holography. So the BTC black hole will be a main focus of our work. So, but in order to introduce BTC black hole on the BT tree, we need a genus greater than 0 p-Adic curve. So if we review how to construct the ordinary torus, we see that we have two ways. The first one is to identify it with a complex lattice. as follows. So tau becomes the modular parameter of the torus. And the second one is that we can quotient the hyperbolic 3 manifold by a Schottky group. And then the conformal boundary will become the torus. And the tau is the same in these 2 bullet points. So in the p-adic setting, the first one does not really work. So one has to resort to the second way of construction. So again, we need some p-adic Schottky group generated by this diagonal matrix. And then, as we have seen before, the total space is the BT tree union with the conformal boundary with this limit set, these bad points removed. So the thing in the big parentheses would be the genus 1 boundary for the BTZ black hole. And one can quotient the total space by the Schottky group. Then the resulting graph, which is no longer a tree, has one regular polygon at the center. So it is identified with the BTZ black hole. So it is done in the 2016 paper by the Caltech group. And the horizon length is just the number of edges, which is the base p logarithm, the usual logarithm of the p-adic norm of q being the modular parameter. So here is an example of BZ black hole with horizon length 4 and prime being 3. So the terminology is as follows. So the genus 1 is usually called the Tate elliptic curve, and for high genus is called manifold curve. And in this talk, we'll only focus on the first one. So that is the bulk of in the bulk side of p-adic holography. And on the boundary side, we need the p-adic CFT. And there are a set of axioms laid down by Melzer back in 1989. So as usual, we have the OPE algebra for the p-adic CFT. So the OPE coefficients are all real, and the correlation functions are complex valued. And the conformal transformation is, as usual, fractional linear. So to go from x to x prime, we transform it according to this rule. And it is easy to show the red identity, namely all the fields are primary fields. And here dx is the Haar measure on Q sub p. So in the same paper by Melzer, the axiom says that the primary operators can have arbitrary dimensions, but the identity operator should always have dimension 0. And here are just the results for 2-point and 3-point functions. And the p-adic CFT is automatically unitary, unlike its Archimedean cousin. And since there is no local conformal algebra, basically means that there's no non-trivial derivative over the p-adic number. All the OPEs are exact. So if you write down the OPE, there's no usual ... And so basically all the conformal information is encoded in this global conformal group, PGL2QP. So it does not have a conformal algebra, which I will come back in the last section. And the p-adic holography is first established back in 2016 and using propagators and correlators. So here I just list the results of the results for ordinary holography and p-adic holography side by side, and you can see that those formulas are very similar for each of these key ingredients. So these formula are not important at this point. So this is just to show that the foundation is laid as follows. And then, so here we have 2-point and 3-point functions. So for 4-point function, it's much simpler than the ordinary one, basically due to the ultrametricity we talked about earlier. And in the unramified extension Q sub p to the n, the operator due to the edge length fluctuations on the BD tree has 2-point functions as follows, which implies that the dimension of t is n. N is the same as the n in the subscript, well, which is as expected for stress tensor, but there's still no spin 2 particle on the BD tree because the state of art is only introducing U1 gauge field on BD tree, and most of the foundational work are done for scalars. So besides these traditional holography quantities, the p-Adic holography also passed several other checks, such like Liu-Takayama formula in computing the entanglement entropy, and like MERA, which is the tensor network formulation. So this can be seen in these 2 papers, among several others. Okay, so here, so basically I concluded the introduction and motivation and all the background informations. So later I will talk about the bulk computations in our work. So key starting point is the GKPW dictionary for ordinary ADS CFT. So this is credited to the 4 authors in 2 separate papers back in 1998. So one of the main formula of the dictionary is as follows. So on the left-hand side, we have the gravitational partition function in the bulk, which is about the semi-classical gravity. And on the right-hand side, it is the generating function on boundary CFT. And phi here plays the role of source, and O here is CFT local operators. So it is true if the boundary condition satisfies as follows, as you move towards the conformal boundary. And then by setting the source to be 0, the generating functions on the right-hand side should compute the CFT partition functions. Yes? Okay, maybe it's not a question. So here, schematically, we can write the gravitational partition functions as follows. And the action in the exponential can be written down in this equation for massive scalar fields with source. And the subscript A labels the vertices on the BD tree. So in the first summation, the angular bracket denotes the summation of adjacent vertices, and the J sub A plays the role of source in the action. And then the linearized equation of motion is as follows, where the box operator is the lattice or graph Laplacian, which is a positive definite operator defined as follows. So for vertex A, you sum over all the difference between all the field value at A and all the adjacent field values. And now the partition function is simply the 1 over the square root of the determinant with 0 modes deleted. So to compute this, we need the eigenvalues lambda I of the Laplacian. So first we'll focus on the massless case, so M can be ignored in our following computation. So I would like to point out that there's another way proposed to calculate this partition function. So it is based on the techniques from tensor network and by making analogy with ordinary diagonal two-dimensional CFT. So to compute the following quantities. But we will not follow this proposal, and overall calculations are from the bulk. So let's first look at the thermal ADS, which is a truncated BD tree. And all discussions will be on massless scalars. So this is the thermal ADS. And in the following slide, it will be somewhat technical because there are a lot of recursion relations. So we see that the BD tree is homogeneous. We can actually pick the center and assign any vertex with depth n, namely the number of edges away from the center, whose depth is 0. So this arbitrariness is also alluded to by in Bogdan's talk. And we can show that there's no angular modes in this thermal ADS space. So to show this, we just take the boundary value, field value to be 0, and then we use the following recursion relation derived from the definition of the Laplacian, and then we move backwards from the from boundary to the center, and then if we look at the fixed field value at depth n-2, we get the following equality. So the tilde means the phi is on a different branch from the phi. So we get isotropic field values around the BD tree. And then here we consider the source to be 0. Namely, here we turn off the source. And then we start from the depth 2. We have this recursion relation. Then we have the initial, so phi naught is the field value at the center, and we have the 2 initial conditions. And because this is a linear order 2, a linear second order recursion relation, we can solve it by solving the quadratic characteristic equation, which gives us the root alpha, and also in combination with the initial condition, we can solve for the coefficient. And then we can express the field value at any depth n as follows. So it is a polynomial in the eigenvalue lambda. And the facts are the coefficients of the highest degree term is as follows, and the coefficient of the constant term is always phi naught. And then simply by the Viet formula, we can see that the product of all the eigenvalues of the Laplacian is p to the n plus p to the n minus 1. Okay, so it looks divergent if we send n to infinity. So the same divergence takes place if you count the number of boundary points, which goes like this as n goes to infinity. So now let's step back and recall some common divergences in the ordinary ADS3 CFT2 computations. So first, if we compute the one-loop determinant of the same operator for massive scalars on the hyperbolic 3 space, we will get something like this. So it includes both UV and IR divergences. So this volume, the total volume of the spacetime is the IR divergence, and the T, which is which you encounter in the computation, if it goes to 0, it is also divergent. So it is a UV divergence in some sense. And then on another occasion, for on-shell Einstein-Hilbert action with constant metric, as follows, we also encounter the IR divergence. So it is resolved by introducing a renormalized volume which is introduced by Kranov in 2000. So the epsilon is the distance towards the conformal boundary. So if it is 0, you are at the conformal boundary. And all the above-mentioned divergences can be removed by local counterterms. So now in our case, the boundary area, namely the number of boundary points, shows up in the exponential of action instead of the action. But the volume of the bit tree grows exponentially instead of according to Power law. So we propose that the regularization gives us the partition function of the bit tree as follows. So we simply divide the product of all the eigenvalues by the number of boundary points to get this result. So we can look further into the detailed spectrum of the Laplacian operator on this truncated bit tree. So the following are several numerical observations as n goes to infinity at a fixed prime number p. So first is that the upper bound on the smallest eigenvalue and the lower bound on the largest eigenvalue as n goes to infinity, they converge separately. So they converge to two separate values. And it is done by Newton's method. And we observe that the decay of the field values phi sub n is almost exponential. So here we plotted two sample graphs of the real part of the logarithm of the ratio of field value at depth n over the field value at the center. So you see that it is almost a straight line. And after removing these exponential envelopes, we see that the field values oscillates around 0, and it fits perfectly with the sinusoidal curves. So now, based on this second and third observations, we propose the ansatz for an effective formula for the field values at depth n, giving the ith eigenvalue. So as follows. So in this equation, k and psi, the phase, the shift to be determined. So along with the previous recursion relation, something like this, we can show that the eigenvalue satisfying this relation. But what about the k in the cosine? So in order to see what is k, we plot all the eigenvalues in the descending order, from the largest one to from the smallest one to the largest one. And it is easy to see that the k is 1 because there's basically no oscillations over the range from n equals 1, from 1 to capital N. So the blue box equation is exact only if the corresponding field value is given for large n and then goes to infinity. So it is somewhat different from the plane wave basis in the Caltech group, in the paper by Caltech group. So this plane wave is also alluded to in Bogdan's talk. So due to this oscillation and the exponential decaying behavior, we call it an evanescent wave basis. So that concludes the computations on p-Adic thermoideal space. So any questions so far? Okay, so then I'll move on to p-Adic BTZ. So again, the recursion relation will be our key technique. So unlike the p-Adic ADS3, the p-Adic ADS, there's a new feature, namely the field values on the horizon. So as we have seen before, we have this horizon, which is a regular polygon. can be different. So we can take L different values, and we use S to label the horizon vertices, and also the subtrees rooted at horizon point. So again, the boundary field value vanish, and then the initial condition from the boundary is as follows. So here is there is a subscription. Here is a subscript T, which will become clear soon. So now we do the linear recursion from the boundary towards the horizon. So from the outside to inside, same as before. So this is the same recursion relation we have encountered here, but only with the reverse direction. Okay. Again, we can solve the quadratic characteristic equation. We get the field values for at any depth. And then we denote the ratio between the field value at depth 1, so namely the field value at depth 1, just one step away from the horizon, and the field value on the horizon as k. So it can be shown that it is isotropic around the horizon, but it still depends on this root to the characteristic equation, and thus the eigenvalue lambda t, because the lambda appears in the coefficient in the linear recursion relation. So we write the k as a function of lambda. So now we do the recursion relation around the horizon. So now it becomes as follows, with a periodic boundary condition that field value at the point 0 equals the point L on the horizon. So again, we solve the characteristic equation as follows. And then due to the periodic boundary condition, both roots have to be a root of unity, which constrain the k of lambda to be as follows. So we see that there's a twofold degeneracy due to these cosine functions. And now the label t the minimum label t becomes clear. It labels the oscillation modes around the horizon. It turns out that the product of all the roots, all the roots all the roots to the polynomial, which is the value of the field at depth n, for fixed t, for fixed oscillation mode, is as follows. And then because t can take L different values, we need to, in order to compute the determinant of the Laplacian, we need to multiply all contributions from all possible values of t. So here is a key identity. If you multiply something like this equation, cosine plus additional term, you can express it in terms of the Chebyshev polynomial of the first kind. Okay, then there's a somewhat weird feature that the result will depend on the evenness of the horizon length, basically due to the range of possible values of t here. And due to the twofold degeneracies, we need to take this cell function. And then, so here is the result. We see that it is diverging as p to the L times n as n goes to infinity. So this divergence is very different from either the growth of number of boundary points, which is this one, or the growth of the total number of points on the entire PTZ graph, which are both linear in L instead of being exponential in L. So there is no obvious way to regularize up to now, and we keep our results as follows, which are unregularized. So this remains an open question in our work. Okay, so to summarize, in order to reach this result for p-adic BDC, we do 3 different recursion relations. So first we go from boundary to horizon using this blue recursion. And then we go around the horizon using this yellow recursion. And finally, we go from the horizon to boundary using the same equation appeared in the thermal ADS. So here concludes the results on the massless scalars on thermal ADS and BDZ. Okay, and then we can do some more calculations for massive scalars. So again, this result is obtained by the 2 papers back in 2016. So there's a nice relation between the prime number p, the conformal dimension, conformal dimension of the operator dual to the scalar, and the mass of the scalar. So where the zeta sub p is the so-called local zeta functions. And again, similar to the usual ADS3, it satisfies this BF bound, namely the most negative value of the mass squared is as follows. So it is a bit weird at the first glance because the mass squared can be negative, but it is stabilized by the negative curvature of ADS. So this also shows up in the p-Adic holography. And then as follows, we can compute the same quantity, the partition functions for the B tree and BTZ graphs, perturbatively for those massive scalars. And the result simplifies as mass goes to 0 and when mass goes to infinity. And here, all of them are unregularized. And for the regularized version, it is written in the paper. And the capital A, B, C, D are just some rational functions of the mass, the truncation depths of the BTZ, and the prime P. Okay, so that concludes all the computations on partition functions. So I guess I should pause for any possible questions. Okay, so now we would like to look at the p-Adic CFT from another point of view. Again, by resorting to the p-Adic bulk spacetime. So our motivation comes from this one loop Witten diagram. And before talking about the Witten diagram, let's step back and look at the ordinary 2-dimensional CFT. So as is well known, the modular invariance is very crucial in the theory of 2-dimensional CFT. So it constrains the form of the partition functions, which gives you some combination of modular forms, and also the spectrum of the operator dimensions. So in the bootstrap community, the modular invariance also plays a crucial role. And specifically, in our work, the Torus 1-point function of the CFT can be used to estimate the high temperature spectral density of the theory weighted by the OPE coefficients. So in particular, we look at this quantity. So holographically, so up to now, it's a purely boundary CFT discussion. And holographically, the state E is a high energy state. It is due to the semi-classical BTZ black hole in the bulk. And in order to probe this BTZ black hole, there's a nice thought experiment proposed by Maloney, Per Kraus and Alex Maloney back in 2016. So one shoot sorry, so first we denote the O and chi as slight primary operators in the CFT due to two light box scalars, phi sub O and phi sub chi. So they're light because the energy is very small compared to the central charge, which is large in the semi-classical holography. And then in their setup, one shoot the scalar phi O from the boundary towards the horizon of the black hole. And near the horizon, it split up into two particles, namely two chi, and they go around the horizon for many cycles. And one comment is that those two box scalars are not conical defects, so they are in some sense real matter in the space-time. So one important quantity is this averaged 3-point coefficients, which is defined as this OP coefficients divided by the density of the state at energy E. So it is average in the sense that it is taken over all the states with the same energy E. So the denominator, the density of state, is given by the famous Cardi formula in 2D CFT. And the numerator for ordinary two-dimensional CFT can be easily calculated as a trace of the partition function inserted with the operator over the Hilbert space of a thermal circle. So its asymptotics is as follows. So it is exponentially suppressed by the radius of the horizon. So R plus is basically the radius of the black hole. And on the other hand, it can be computed from the Witten diagram. So Witten diagram is basically the integrand is the bulk-to-bulk propagator and multiplied by bulk-to-boundary propagator. And the integration range is the entire space-time. So the bulk-to-bulk propagator in this case can be obtained by method of images because, as I have said before, the chi field can wander around the horizon for many times. And here the sigma n is just the geodesic distance between the space-time point and its nth image. Okay, so let's turn to the p-Adic setting. So in p-Adic, due to the discreteness of the bulk, we cannot do integration, and instead we do the summation as follows. And now, in order to be more convenient, we reparameterize the BT tree by these two parameters. So n is binary, 1 is 0, non-zero, and h is as usual, is a depth on the BT tree. So for 0 n, it means that for the boundary to bulk propagator, it means that the boundary point x and the bulk point on the horizon are on the same subtree as follows. And if n is non-zero, it means that the boundary point where you're shooting the phi O scalar is on different subtree from this from the horizon point of your concern. So in the p-Adic settings, the both green functions are basically known. This shown in these two papers back in 2016. And in our case, we use the method of images to get the renormalized boundary green function. So by renormalize, I just mean that there's some additional terms which can be removed by the local counter terms. And so this is for chi, because the chi is going from bulk to bulk. And sorry, for O, which is from boundary to bulk, we have the following Green's functions. So one caveat is that we need to regularize the geodesic distance. So by dictating that this distance is 0 if x is in the same subtree rooted at point C on the horizon. So this regularization was first introduced by Zabrodin, and then it is shown to be consistent with the p-Adic holography by this group, by this paper by the Caltech group. And then we basically sum over we sum up the two contributions for n equals 0 and being non-zero. And then by taking the large horizon length limit, so namely the length is very large, we get the average 3-point functions as follows. So if we compare this expression to the expression here, we see that we are missing an analog of this exponential factor. So basically e to the minus radius. Oh, sorry, basically, sorry, we're missing the radius to the conformal dimension here, this factor. So it is a bit mysterious, but we have an intuition for this missing factor. So basically, it means that the scalar field phi O is unable to see the radius of the p-Adic BTZ. So by shooting in a phi sub O scalar field towards the BTZ black hole, it is hard for it to see the radius of BTZ, the radius of the horizon, because the horizon is basically given by the length on the graph, and there's no well-defined radius in this setting. And we expect that this relation should hold true for all p-Adic FTs. Okay, so any question for the second part? All right, so that concludes my second part, and for the last part, which is a small section, we explore a bit into the possible representations for the p-Adic FTs. So as we all know that there's trouble with the Lie algebras. So again, back to the ordinary two-dimensional CFT, it would be great if we can compute the one-point functions, this one, as usual. So this is the way of computing the one-point function in the usual 2D CFT, basically in the operator formalism by taking the trace over the Hilbert space. But unfortunately, the exponential map from the global conformal group PGL2QP to this would-be Lie algebra does not exist because the p-Adic exponential defined as follows diverges at identity. So it is impossible to perturb around the identity. Yeah, also because of the radius of convergence is as follows. So the Hilbert space curly H cannot be a representation of an algebra as usual, but we still want a group representations. So in recent progress, this
sorry, you should go to the conclusion. You have only 7 minutes, including.
Okay, so maybe
questions.
I'll take like 3 more minutes to go to the last slide.
Mm-hmm.
Okay, so in separate contexts, like in two-dimensional JT gravity, the group representation of the gauge group plays an essential role. to determine the spectrum of the theory. So since all the p-adic CFTs are unitary, we would like unitary reducible representations. And since all irreducible representation of PGL2QP naturally induces an irrep of GL2QP, so we will study the latter one, and then one can just canonically restrict it to the projective one. So here we we summarize all the relevant representations in this Venn diagram. So we would like these admissible representations, namely both smooth and irreducible, which is the intersection, the overlap between the two big circles. So we would like to narrow down in this Venn diagram. So first, all the finite dimensional smooth representations are trivial. They're just one-dimensional complex vector space where the GL2QP images act like a scalar multiplication. However, it is likely that an ensemble of primaries of the CFT can be viewed as a tensor product of them. Anyway, the infinite dimension representation is more desirable. So there's a trichotomy and classified into the supercuspidal one, the principal series, and special representations. So the first one is desirable because in some sense they are the most native representation of GL2QP. And the principal series and special series the special representation can be derived from it. And it has a nice inner product. And also it behaves like representations of an ordinary compact Lie group. Okay, so now we propose to restrict our attention to this small orange region. And now, normally in the two-dimensional CFT, the summoned the Virasoro character on the torus is as follows, which is basically a square root of these partition functions. Can be viewed as a representation of the dilatation transformation, namely the generator of the Schottky group. So in the p-adic setting, we would want that the partition function of the p-adic CFT can be expressed as certain trace of the representation of the Schottky group. Okay, so this is one criteria we proposed. Okay, now for the outlook. So again, as I have said, the regularization for p-adic BTC black hole is unknown. Maybe one need to resort to some p-adic version of RG flow. So it is talked about in this 2019 paper and also in the earlier talk by Malik. And one can look into the detailed spectrum of BTC black hole. And again, so up to now, we only talk about scalars, and it is desirable to talk about like true diffeomorphism, both large and small on the BD tree. And also one would like to introduce other degrees of freedoms like gauge field and supersymmetry fermions on the tree. And incidentally, I don't know if there's a connection with the spin glass because the ultrametric space also show up in the phase space of the spin glass. And last but not the least, we need to pinpoint the representations, group representation for p-adic CFTs. Okay, so that's the end of my talk, and thank you for attention.
Yeah, well, thank you.